Next talk, we have Hossein Hafezi. Talk, yeah, he's changed affiliation since the first talk, and talking about single server outsourcing of ZK SNARKs.
Thank you. Yeah. Uh-huh. Hey again, everyone. Yeah, so I'm going to be talking about single server private outsourcing of ZK SNARKs. Joined work with Kastra, Sarah, and John. Unfortunately, they couldn't be here today. So I don't really want to review that again, but we got a public relation R, which is an MP language, and we got a prover and a verifier, such that the verifier has, both verifier and the prover have the public instance, whilst only the prover has the witness. And it sends a proof such that it satisfies completeness, knowledge soundness, zero knowledge proof, and blah, blah, blah. All right. As you may know, there is a lot of interest in zero knowledge proofs, and they've been already deployed in practice. These applications include private transactions, such as Zcash, Sing Sing blind chase, such as Mina, and anonymous credentials, which is quite a hot topic right now, due to the EU regulations and the EU grants, at least in Europe, every group is working on them. I can go on forever talking on applications of zero knowledge proofs and why they're useful, but what is the actual irony? It turns out that proving a computation is way more expensive than naively just running it, and hence the prover computation and memory generally tends to become the bottleneck. For example, hashing 100 kilobytes of data on a laptop takes only 1 millisecond, whilst proving that can take up to 20 minutes with Euro 16 on a laptop. And basically, there are applications where the prover cost will be essentially the bottleneck, especially in privacy applications, where the client is really the prover. And it includes, for example, ZK login, where a mobile phone is trying to prove something to a powerful server. So the question here would be, can we outsource this proof generation from a mobile phone or a laptop to a powerful server to basically lower the prover's workload and latency? So one naive approach is that for the client to basically send both the instance and the witness to the server, and then the server would run the prover algorithm itself and return the proof. And there's a line of work that they say, if the server is really powerful, for example, a cluster of machines, the proof generation can be done, for example, 100x faster. But the caveat is that the powerful server really learns the private witness here, which might be undesirable for privacy applications such as anonymous credentials. So ideally, we want the powerful servers to be untrusted. So even we can have something like a prover's market, where a client with lightweight devices can offload their computation basically to the market and get the proof without actually exposing the witness to anyone. This is basically the ideal cloud model for the ZK SNARKs. And if I want to summarize what we really want from this proof delegation is that, first, we want the powerful server that doesn't learn the underlying witness. And second, which was basically ignored in all the prior work, is that we cannot really link a proof to a particular transcript. Otherwise, you cannot use it for some applications such as Zcash. So we can think of it as the client sends an encryption of the witness to the server, and the sender server returns an encryption of the proof, where the client can decrypt it. In cryptography, we mainly have two approaches, two tools for computation over encrypted data: fully homomorphic encryption, FHE, or secure multi-party computation, MPC. In the second approach with MPC, the client secret shares the witness and sends it to a number of servers. These servers run an MPC protocol between themselves and then return the secret shares back to the client, and client can reconstruct the shares and reconstruct the proof, basically. And similar to non-private schemes, these approaches have a very low latency and an efficient client because the client only runs the secret sharing protocol. And however, the key limitation here would be basically a threshold of the servers have to be honest because of the underlying MPC assumptions. In the other model, client encrypts a witness under an FHE scheme and sends it to the server. The server runs the prover computation over the encrypted data and sends the result back to the client. And then the client only has to run the decryption algorithm to obtain the final proof. Again, the client in this setting does minimal work because it only runs decryption and encryption. However, the main barrier of this approach, which is not quite practical, is that they do not really reduce the latency of the protocol. And actually, they increase that, as like the latency of the proof generation is increased by 10x, even though the client is not doing a lot of work. And the reason for that is basically an FHE operation can be 10,000 times slower than a native computation. And finally, it's not really clear how to extend this model to support security under a malicious server and the proofs to be unlinkable, because the server somehow already sees an encryption of the proof. And if I want to give you a quick comparison to the prior work, as you may see, most of the existing schemes are multi-server because they're based on MPC, except for our work and BlindFry. And these approaches generally require 2 or more servers. Some of them, for example, require more than 8 because they use pack secret sharing. None of the prior works really considers or achieves unlinkability, which means that it's not basically secure to use them for private transactions, though I think it's already used in industry. And finally, BlindFry is the only other work which is in the single server setting. However, it does not achieve any speed up, and it does not achieve a malicious server as well, due to the FHE problem I just mentioned. And finally, we have our work. So we only work for the group-based ZK SNARKs, and we are basically the first work to consider this unlinkability notion. All right, let's get into the paper. So to list our contributions, we basically have a framework for private outsourcing of group-based ZK SNARKs, which supports latency reduction, security under a malicious server, and unlinkability. The primitive underneath our scheme is called EMSM, which basically helps to outsource an MSM to an untrusted server. And we built this primitive using the LPN assumption. So just to quickly review what an MSM is, I'm sure everyone knows it. Imagine we have a vector of group elements G, we call this the base vector, and we have another vector of the same size Z, which basically consists of field elements. Then the MSM of G with Z is basically the product of G sub I to the power of Z sub I. The main observation in our paper is that the prover computation in all these popular group-based ZK SNARKs is just dominated by the MSM. For example, in our experiments, we found that for Nova, 97% of the computation, and for Garo 16, something like 91 to 92% of the computation is only the MSM, and the rest is like the FFTs and the field operations. And I also want to quickly point out that if we try to use the generic FHE approach, that's going to be quite expensive, because a single group exponentiation is going to be 3,000 arithmetic constraints. That's just basically impossible. So our high-level idea in the paper is that we use the linear structure of the MSM to fully outsource it to an untrusted server, such that the client is only left with the field operations. We'll see the details in the next few slides. Before I tell you how the MSM works, I quickly want to go through the dual LPN assumption. So the dual LPN assumption says that if we got a public matrix H, then H times a sparse vector E is computationally indistinguishable from a uniformly random selected vector B, such that the vector E here is a sparse noise coming from a Bernoulli distribution, meaning that the noise here only has constant non-zero entries. And the way that we build the EMSM from the dual LPN assumption is that, so we already know this linearity property of the MSM, that fixing the base G, then the MSM of Z plus R is equal to the MSM of Z plus the MSM of R. And imagine the client wants to outsource the MSM of Z here. So if the client if it has already computed or can locally compute the MSM of R, the simple idea is that the client can really just send Z plus R to the server. And yeah, because it's already got the MSM of R, it can basically compute the MSM of Z with the subtraction. Oops. But the problem is that, like, if the client can already compute the MSM of R, why computing this MSM of Z is pretty much the same computation. So it shouldn't be hard for them. And then here we use basically this property of the LPN that we replace the the R vector here with an instance of the LPN. So if R is equal to H times the error vector E, then we observe that the MSM of R can be computed very efficiently by a quick change to the base vector. It's going to be equal to the MSM of H transpose times G, and then with the vector E. And because the vector E is like pretty sparse, this MSM requires only constant number of group operations. And yeah, because E is sparse, the MSM is going to be quite efficient. And this new base vector H can be basically pre-computed. We can assume that H transpose times G is just computed during the setup. But we are not done yet, because if H has no structure, then it requires quadratic group operations to do this pre-processing, which can take like days or weeks for an MSM of size 1 million. And for concrete instantiation, we basically use the dual LPN with the RRA codes. If I want to tell you how the RRA code matrix generator really looks like, so H would be equal to a multiplication of these matrices, FR, M sigma 1, A, M sigma 2, and A, such that, just giving you a quick intro of these matrices, the matrix FR is basically a repetition matrix, meaning that when you apply it on a vector, it expands each entry R times. The matrix M sigma is a permutation vector, which operates a permutation sigma on the vector. And finally, A is an accumulation matrix, which is basically an upper triangle matrix such that all the non-zero entries are ones. And when you apply it, for example, on vector x, y, z, you're going to get x, x plus y plus z. And you can basically see that when we use RRA codes as the concrete instantiation, the client for an MSM of size n only does 12 times n group additions and a constant number of group operations. So if I want to really summarize the whole paper in one sentence, is that we basically replace an MSM of size n with only like 12 field additions, and that's it. And yeah, also the setup is untrusted and can be performed by anyone. So I just have like one quick slide left on the security of the RRA codes. So at the time of writing this paper, which was like 9 months ago, I think, the RRA codes were only analyzed for binary fields due to Blaze. And we sort of had to do an empirical analysis over any arbitrarily finite field in the paper. But recently there was this paper which does this analysis more concretely for any large finite field. However, we believe like it wouldn't really change our concrete costs in the paper. But yeah, that's something to look into. And we already got the EMSM. So if I want to tell you how we can build the server-aided ZK SNARK from the EMSM, as you may all guess, is just we outsource every MSM to the server, and then the client can do all the field operations itself. And we see that it's quite compatible with like Garo 16, Planck, Nova, Sonic, Hypernova, KZH Fold, etc. And the reason, because it's going to be cheaper, is because just every field addition is almost 10,000 times cheaper than a group exponentiation, meaning that we really send the price of the MSM to 0. So you only have to do the field operations as the prover. And yeah, it also supports malicious security with this like really easy trick that I've seen in MPC a lot, is that the client chooses a random scalar C and then outsource both Z and then C times Z to the server and gets both MSMs and simply checks that this linear property really holds for it. And finally, we have implemented it for Nova and Garo 16. So for Nova, because more % of the prover computation is really About the MSM, we see that a 20% improve, through 20% less client active computation and a 10x improvement for the latency. For Goro 16, because of the FFTs. So in Goro 16, there are like 6 FFTs. I remember we could like outsource 3 of the FFTs in the paper to the server as well with some of the techniques we had in the appendix. And 3, the client had to do itself. But yeah, we got a 10x reduce in the client active time and a 6x improvement in the latency. And giving you the conclusion, we don't know the conclusion, but for the future work, yeah. So an interesting future work, I think, is more concrete analysis of the other rate codes over any large field. And finally, memory improvements. So our work has almost 0 memory improvement for the client. So I think it would be quite nice if we can do some memory improvement as well. I think, I mean, essentially it's possible with all these like streaming papers and everything, but someone's got to implement it. Thank you. I promise I'm going to be leaving. No more talks.
Thank you. Any questions? Yep.
Am I good? Okay. Thank you very much. Yeah, it seems like you alluded to it, but I guess there's related techniques you can use on the polynomial multiplications that you can use along with this to reduce the overall time of the entire proving system.
As you're saying, like we outsource the polynomial part of it only?
So obviously this is for the MSMs, but you said there was some stuff in the appendix for like the...
For the FFTs.
Yeah.
For the FFTs, basically, yeah.
Okay.
Because any FFT is just like one public operation. Like it's just a matrix operation on a public vector, right? So with this sort of with the same pre-processing, you can just like change the base again and apply that FFT on the base directly during the setup, and then it's basically outsourced to the server as well. So you don't really have to do the FFT yourself.
Gotcha. Thank you.
All right, let's have one more question and have the next speaker get on, yeah.
Hi, thanks for the talk. Quick question. You said there's T group exponentiations instead of N that the client has to do, right? And T is, I assume it's like a small number.
Where was D again? You mean T?
T.
Oh yeah, T. So T is like a constant. For example, for an MSM of size 1 million, it was like 500.
Okay.
So it's like basically constant size, yeah.
Okay, so am I right in saying that if the MSMs that we are doing in proving, which are full size, like the whole column has large values, like for example, permutation, ZPerm, the permutation polynomial, that is full size. So your technique would benefit there more against, let's say, some column that is already sparse or that contains smaller values. The MSMs for that is not really that big.
You. Yeah, so basically there's this thing with the MSMs where like if the witness is sparse, like the cost of the prover would be less.
Yeah, exactly.
So if you have like less cost for the prover, it may be like it's already efficient. You don't want to be like outsourcing it to anyone.
Yeah, exactly.
But for Gero 16 and like Planck, because they use the quotients, like even the witness is like low size, you can't really like take advantage of that. But that's true.
Yeah. Okay. Thanks.
All right, let's thank the speaker again.
Thank you. Thank you. Good luck.